Hello everybody, welcome to your Topic 6 Ticket to Retake. So this video will go through how to do all the problems on this ticket, and please check your answers with it, jump around to specific problems you could use a little more reteaching or reviewing on, and good luck on your retake. All right, so number one, write the following using rational exponents. So a rational exponent is an exponent that's a fraction. This is radical notation right here. It consists of a few parts. We've got this number underneath the radical. That 6 is going to end up being the base in our exponent form. Now we're going to create a rational exponent, or an exponent that's a fraction, using these two numbers. This 7 is the power. This 3 is the root. So I'm just going to label those power and root. All right, so when we go into exponent form with a rational exponent, that 3 and the 7, we create a fraction, putting the power in the numerator and the root in the denominator. So it's always power over root. And that is rewriting it using a rational exponent. All right, so our next example, the fifth root of 2. So this 2 is going to be the base in exponent form. It is being raised to the first power if it helps to write in the exponent. Now I can see we have a power of 1, and we're taking the fifth root. So our rational exponent, we're going to do the power over the root. The power is 1, the root is 5. All right, next example, we're going to bring down the 9 from underneath the radical, and then we need the power over the root. The power is 5, and the root is 6. All right, now this next one, I can see we've got our 13 that we're going to bring down. I can see that the power is a 5, but what we're missing over here is the root. It's not written in for us. So this radical symbol right here, the very first time you learn about that, you learn that we can call it a square root. It's a square root when we're taking the second root. So if they're not writing a number in here for you, then go ahead and put in a little 2 if that helps you. The second root, or the square root, means we are taking the second root, so the root is a 2. All right, so we're going to take the power, put it over the root. The power is 5, the root is 2, and there's our rational exponent. All right, now we're going to go backwards from what we just did. We've got rational exponents, and we're going to put this into radical notation. So radical notation, we do our radical. The base of your exponent is the number that goes underneath, and then we need to identify the power and the root. So just a reminder, this 1 is the power, this 2 is the root. So the root always goes in the little nook of your radical. So the 2 goes right there. The power is 1, and that's an acceptable answer like that. You could go ahead, anytime it's a second root, you don't have to write the 2 in, so you could just leave it like that. Here's our 3, and then to the first power, you don't even have to write in the 1. So these are both acceptable answers for that 3 to the 1/2 power. All right, next we have 4 to the 10/3. So here's our radical. The 4 goes underneath. The power goes with the 4, so 4 to the 10th power, and the root goes right there. All right, 11 to the 5/3 power, here's 11. We're going to keep the power with the 11, so 11 to the 5th power, and the root of 3 goes right there. And then last we have a 6. The power is 11, the root is a 2. And then that 2 is optional. You also could write the square root of 6 to the 11th. All right, number 3, we've got 3 equations to solve. Let's see if I can get this all to fit right here. Maybe write small just to be on the safe side. So We can use, well, first of all, here's an equation, right? We need to solve for x. What we want to notice is that x is in a different spot in our equation. It's up here in the exponent position, and you guys have never been asked or have never learned how to solve equations where the variable is an exponent. So one method that we show you guys in Algebra 1 is how we can use our properties of exponents to make this easier for us to solve. Now we can only apply the properties of exponents if we're dealing with the same bases. So if you look at this first example, you might notice that we have a 10 to a power times a 10 to a power equals 10 to a power. 10, 10, 10. That's our goal. We want those all to be 10s so that we can use exponent properties. All right, our first property tells us if you are multiplying the same base of 10, we keep our base, and then we can either add, subtract, or multiply those exponents. And what we do when you're multiplying the same base of 10, we are going to add those exponents. So I'm just going to write x over 3 plus 3 equals 10 to the 5x power. So now we have 10 to a power is equal to 10 to a power. Well, we know that 10 is equal to 10, right? This is an equation, so this is equal to this. So if the bases are the same, what that means is that these exponents must also be the same. So what we do is we write a new equation where we set those equal to each other. And now we have an equation where we are able to solve for x. It's no longer an exponent. We can actually get to it and do our solving. So for this problem, first thing I notice is we have a fraction. I'm going to get rid of the fraction by doing our fraction trick. We can multiply everything by the denominator. So 3 times x is 3x. 3x divided by 3 is just x. 3 times 3 is 9. And 3 times 5x is 15x. All right, now solving for x, let's just get those x's to the same side. So we have 9 is equal to 14x, and then our last step, we're going to divide by 14. 9 does not divide by 14 evenly, so we're just going to leave that as a fraction, 9/14. All right, our next equation, we need to solve for x, and we notice that x is an exponent. So we have to find a new way to solve our equation. What we would like to do is use our exponent properties, which we're allowed to do if we have the same basis through the whole equation. So this is 7 raised to a power is equal to 7 raised to a power, which is not written in, so if it helps, go ahead and just make that a 1. I like to see that 1 right there for a problem like this. All right, so we have an exponent property that says if you have a power raised to another power, so it's our power to a power property, what we do is we keep our base and we multiply these exponents together. This will probably feel like distributing. The 3x plus 2 is getting multiplied by 4, which means the 3x gets multiplied by 4 to give us 12x, and the 2 gets multiplied by 4 to give us 8. I'm just going to carry down equals 7 to the first. All right, so now we want to recognize that we have 7 to a power is equal to 7 to a power. These two are equal to each other. It's an equal sign. So when your bases are the same, that means that our exponents will be the same. So what we're going to do is we're going to write a new equation with the exponents. All right, so solving for x is just a two-step equation. We're going to subtract 8 from both sides. So 12x equals negative 7. Divide both sides by 12. Let's see, 7 does not divide by 12, so I'm just going to leave the fraction, negative 7/12, which is reduced, so that's a pretty good answer. All right, we have one more equation over here. Solving for x, we notice x is an exponent. So we have a new way to solve an equation like that. What we want to notice is we have 2 raised to a power to another power divided by 2 to a power is equal to 2 to a power. So we have all these bases of 2. On the left, we can do a little bit of simplifying here. Well, first, this numerator, that's a power raised to another power. So we can keep our base. When you have a power to a power, you multiply. So x over 5 times 2 is a 2x over 5. Over 2 to the 4th equals 2 to the 3x over 2. Okay, so now we have a situation where we are dividing the same base. When you divide the same base, you're going to keep your base, and we can either add, subtract, or multiply the exponents. This is the type of problem where you're going to subtract the exponents. So 2x over 5 minus 4 equals 2 to the 3x over 2. And now we've got it set to we've got 2 to a power is equal to 2 to a power. So when your bases are the same, equal to each other, that means your exponents will be equal to each other. So our new equation is 2x over 5 minus 4 equals 3x over 2. All right, so we've got an equation to solve. It's got some fractions, so let's do our fraction trick. We can multiply every single term by the denominator. In this case, we have 2 denominators with a 5 and a 2, so we actually want a common denominator. We're going to use a 10. All right, 10 times 2x is 20x. 20x divided by 5 is 4x. 10 times a negative 4 minus 40. And then 10 times 3x is 30x. 30x divided by 2 is 15x. All right, so solving for x, let's get these x's to the same side. So we have negative 40 equals 11x. And our last step is to divide both sides by 11. 40 does not divide by 11 equally, so our final answer will just be x equals negative 40 elevenths. All right, last problem on the front page. So graph the function and identify the key features. Be sure to plot points and draw the asymptote. All right, so a problem like this on the test, we were asked to fill in a table of values. So let's just go ahead and get our table of values. Very commonly, we're asked to fill in ordered pairs where the x's are negative 2, negative 1, 0, 1, and 2. Okay. And so we're going to plug in an x for all of those. Now, if we just type in like 1/2 raised to the negative 2 power, we get back a 4. If we plug in a negative 1 for the x, so I'm just looking at this function right here. If we plug in these x values to this function right there, we will get back these answers, a negative or a 4, a 2, a 1/2, a nope, not a 1/2, excuse me, that's just a 1. Oops, here we go. A 1, then a 1/2, and a 1/4. One way that you can get this table of values is on the graphing calculators. If you type your function into the y equals, then you can hit second graph to access the table of values, and you can pull out all those ordered pairs that way. So we're going to graph this. Now, when we graph this, we do need to draw an accurate graph. An accurate graph is going to have plots pointed in the exact spot where they go, not just like a random curve drawn. We need to go through these points for it to be accurate. All right, so our first ordered pair is negative 2, 4. Then we have negative 1, 2, 0, 1, 1, and then 1/2, and then 2 and 1/4. All right, so this is a decay function coming down like this. If we do not have any vertical shifting, what it's going to do is going to come down and it's going to look like it's leveling out, almost like it's going right on top of the x-axis, but it's actually getting closer and closer and closer to a horizontal asymptote. So we do need to draw in the asymptote. This is a line that our graph will never touch, so our function will never equal that y equals 0. It's an asymptote, but it will get closer and closer and closer and closer to it as our x's get bigger. So as we move out this way on the graph, our curve here is going to get closer and closer and closer and closer to it. I mean, so close that to the naked eye you can't even tell a difference. But mathematically, it just gets closer, closer, closer. It keeps getting half the distance closer as the previous point. And you could always take a distance and divide it in half, even if it's so minuscule we can't see it. All right, so there's our graph. We filled in a table of values. We plotted the points. Now we have an accurate graph, and we also drew in the asymptote. That's what we're looking for full credit. All right, so let's talk about the domain and the range and the y-intercept and the asymptote. All right, so the domain for these exponential functions is going to be all real numbers. That's because domain is your input, numbers we are allowed to plug in for x, and still have the ability to do this math. Can we raise 1/2 to any power? And you can. You can raise it to a negative power, you can raise it to a power 0, or you can raise it to positive powers. So all real numbers are part of the domain. Now the range is the output. If we take any x value and take 1/2 and raise it to that value, what numbers do we get back? I think a graph is a very good visual to help us with the range. What we notice in our graph is we've got our curve, but it's never going to touch this line, y equals 0, and it's never going to be down here. So all the values in the output for our range are above this line y equals 0. They're all positive. It's always going to be up here. So our range, all the y values will be greater than 0. Not or equal to, because it's never going to touch that asymptote. It's always going to stay above it, which is why we're greater than 0. All right, the y-intercept is where we cross the y-axis. That's going to be this spot right here. I plotted the point. I kind of missed it as I was drawing my curve, but that's at 1. In an exponential function, your initial value, which is right here, remember it's a times b to the x. So our b value is the 1/2. Our a value is the number in front, which is a 1. So maybe we knew it was a 1 from the function, or we could have looked at the graph and confirmed that our y-intercept is a 1. And then the asymptote is that horizontal line y equals 0. It's always going to be y equals 0 unless we shift this graph. If our graph shifts up and down, the asymptote will shift up and down with it.